So we have a square with a current running through it of 10 amps, and it's going around this direction. And the length of this square is 0.4 meters, right? This is how we're going to set up the problem. We're going to use this formula. That's the one in blue. That's the key right there. It's the cross product between the direction of which way you're integrating, dl, which will actually be your dy. Your dy. I'm gonna label this slightly differently. I'm gonna call this distance x, right, from the middle of the square to here, and then call this distance y, and call this dy. And so, because the problem, actually I didn't mention, the problem is asking what is the magnitude and direction of the magnetic field at the center of the square current loop, right? And so we're asking, let's actually tackle the easiest part, which is the direction, right? So there's two right-hand rules. I'll explain them a little bit later. But the second one is the one where you grab. Imagine you're grabbing the wire, but I don't advise grabbing the wire. You have a current running through the wire. So if I align my thumb with the current, then you see my fingers are going to curl into the board or into the page. So the magnetic field, it makes a circle around that wire at a distance x. See, so you imagine at a distance x, it makes a circle going into the board. So at this point, it's pointing inwards. So it's a circle, and then that circle part at that tangent point, right, is pointing in. You see that, guys? So it goes in. And you can check that with this way, right? If I line my thumb this way, it's also going in. And then you can line it this way. My hand's kind of tilted. That way and this way. So it makes sense. So it all works out. So we know it's going to be pointing inwards. Now on to the magnitude. So we're going to go back to this formula here. And this is the cross product. dl, the distance that you're integrating, a piece of that wire, cross r, the r vector is the vector pointing from the piece to the center point. That's the r vector. When you cross that, it's magnitude of dl, magnitude of r, times the sine of theta, the angle between dl and r. And we know that since this is the unit vector r, that unit vector r has a magnitude 1. So you don't see that there anymore. And we said that dl is my dy, because I'm calling this y, so that's my dy. Okay, now we're going to review some trig, right? We know this, right? Sine of theta is opposite over hypotenuse. Right? So looking at this triangle, opposite over hypotenuse. And we know r is x squared plus y squared, the square root of that. Right? So that's given there. 1 over r squared is going to be this distance, r squared. So that's just Pythagorean theorem, x squared plus y squared. 1 over that. So we make a substitution of this cross product here, and then let's take it over here now, and we're going to integrate. So we have sine, we're going to pull out the constants, mu, I, and 4 pi, and integrate from negative L over 2 to L over 2, negative L2 to L2. Sine of theta, replace sine of theta. That's x over x squared plus y squared. And there's also this r squared here, right? That's r squared here is the 1 over x squared plus y squared. That's why we had the 3 halves. That's where that 3 halves comes from. And that's where the dy comes from. And we know x is going to be 0.2. And how do I know that? Well, because the length was 0.4, and it's a square. So half of that, that's how we get that 0.2. That's x is 0.2. So we're integrating with respect to y, and we basically make a u substitution here. And I'm sure you guys know how to integrate. When you integrate this and plug in x is 0.2 and plug in I for 10 amps, and mu, which is a constant that is in the textbook, you're going to get 7.07 microteslas. That's what you're going to get right there. And that's just for that one wire. That's just for one wire. And we have 4, right? So we're just going to multiply this by 4. And that's how we get the final answer, 28.3 microteslas, into the page or into the board. Got that? So that's how you would do something like this on a test. So on the test, I would just remember this part right here. Because if you have a square, you can just jump to this step. Jump to this step. Because you can understand where that came from. You don't have to set that up again. That just kind of tells you where it comes from. But if you have a square and they're telling you to find the magnetic field, just go to this step. And then do that integration, and you'll get it. Okay, questions? Okay, this is a classic problem. Classic problem talking about two wires. So you have two sources of magnetic field. So just like how when you have the electric force, you have two charges, right? You're comparing the force between two charges. Here, we can think of it in a similar manner, that we have two wires. Therefore, we have a force, a magnetic force between two wires. So see, you can't just talk about one wire and talk about the magnetic force. It depends on where you think of it as a test magnetic particle. There's, you have the test charge, you have electric field, you have a test charge. You can think of it as like a monopole magnetic field, but that doesn't exist. You'll learn that in later physics, but the analogy kind of breaks down. But the thing is, you have two wires, and the first right-hand rule is you have a velocity of some charged particle, and you have some external magnetic field acting on that charged particle at that point. And then at that point, that charged particle is going to feel force perpendicular to those two vectors. Okay? So, think of this point there as being a charge. At that instant, at that little point right here, it's a little charge. We're asked to find what is the current in the other wire. And we know two things. One, the current of the first wire. And two, we know that the wires repel. That's what it's given. So you do an experiment, you have two wires, and you put a current, and let's say you don't know what direction the current is from the other wire. You see them repel. Okay, all right, so if they're repelling, we can determine what direction that current is going, and we can determine the magnitude. How do we do that? Take this drawing, look at it in the front view, like this. Again, this is the arrow, right? If you see an X, it means you see the tail feathers of the arrow, so it's in, and a dot means the point of the arrow, it's coming out. So, this current is going in, right? So it's going to go into the board. We know that the force, the magnetic field of this wire from 2 acting on wire 1, and that's the force, whereas this is the force of the magnetic field generated from this wire acting on wire 2. See? And that magnetic field from this is making this charge on this wire move, and vice versa. See? So, if this is the diagram, right? We see this all the time when we grab it, right? This is the magnetic field. It goes in circles at different radiuses, different R's. That's where that magnetic field equation with the 1 over R squared dependence thing came from. Yeah. So here, right here, you see this diagram that as these magnetic fields, you want to look at this point, right here, right? That point. It's a circle in this plane. So it's cutting or touching that point, tangent to that point. So the magnetic field here is pointing down, right? That's the magnetic field from wire 1. So in this diagram, the circle goes like this, and the magnetic field from wire 1 is pointing down. And there we go. We have the external magnetic field. So in this perspective, in this wire, the external magnetic field is wire 1. That's the magnetic field from wire 1. And if this is the direction of the magnetic field of wire 1, the external magnetic field, and this is the force direction, then we have 2 of the 3. What direction is the current going? Let's use our right-hand rule, the first one, right? So, to get my force to be pointing this way, my middle finger, my magnetic field is my index finger, so my thumb is pointing what? Out. That's how you determine it. So, that means the current must be coming out of the board. Like this. That's how you determine it. So, it's a combination of this right-hand rule with this right-hand rule. That one. So, that's how you determine the current. So, if it's coming out, then in this diagram, it must be going this way. The current must be going this way. Now, how do we know the value of the current? Well, here's the, let me box this one. Here's the force. You think of this as the magnetic force, right? It's the current of the wire that's generating it, and this is the external magnetic field. So, this is the wire that's generating it, wire 1, and this is the magnetic field, which is the external one. So, this diagram is vice versa. So, imagine drawing the same thing in the opposite way, too. So, this is magnetic field due to 2. Okay, we were given, again in the paper, that the force per length of the wire was 2 times 10 to the minus 4th newtons per meter. You're just given that. So this is an equation you can divide by L. So now you have this number here, force per length of the wire, is this. So you have that piece. Now I can replace what B is. B is this. Now this is a result from the integrating what is the magnetic field at a point from a wire. That's where this comes from. This comes from, you can check the textbook and see the derivation where that's come from. Okay, so this piece is now plugged in here for B, for magnetic field 2, rearranged to find I2, right? And you get that it's 8 amps when you plug everything in, and this is the value of mu naught. So that's how you find the magnitude and the direction of 2 wires. So, in conclusion, if currents go opposite directions, they repel. And if currents go in the same directions, they would attract. That's the takeaway. So some quiz question, that's how you know. Opposite, they would repel. Same, they would attract. Here we have a coaxial cable, right? And we have a current that's coming out, and currents going in is a sheath. So we have a cable inside a cable. This is used to transmit power. They use coaxial cables. And here we have distances of d, 1 millimeter, and we're asked to find the magnetic field direction in points A and B. So we simply just use this equation, this one that has been derived from a line, and the hard part really is just to determine the direction, but actually it's not that hard. You see that if I use my right hand, if my thumb is the direction of the velocity of the charges, or the current, right, it would go this way, so my fingers would be in a circle like this, and so when I come here, that part of the circle would make that point at point A point up. So that's how I determine that's the point up. So it's going to go up. When you plug in the values, you're going to get 200 microteslas up. And why does current 2 not contribute? Because the magnetic field is emanating from the center of this wire. From this wire, the magnetic field from current 2 is only out here. This magnetic field is out here. But inside that wire, the magnetic field will be 0. So that's why at point A, the contribution of the magnetic field only comes from the current 1. And so we get this. But for B, because now B is outside, both 1 and 2, we can think of current 2 concentrated at the center and current 1 there. You can think of it as just one wire with a net current, right? So the net current, and let's look at this. Well, if the magnetic field is, if the the current is going inwards, then the magnetic field direction is going to point down. So at point B, we can do this. This would be the magnetic field due to 1, and this would be the magnetic field due to 2 at point B. So which one's going to be stronger, right? The net, the total. So at B is going to be, well, I'm going to call this up, so it's positive. I'm going to call this one down, so it's negative, so I'm going to subtract. You could do that, or you could say that the currents are going opposite ways. Just make sure you keep your minus signs correct. And so then when you subtract, you're going to get 133 microteslas. And that's how you determine things like this, the coaxial cable problems. All right.